Hello, my name is Tiffany, and today I will be talking about the Fibonacci sequence and the golden ratio. The golden ratio is a particular number often encountered when taking the ratios of distances in simple geometric figures. The golden ratio is equal to 1 plus the square root of 5 all over 2, and denoted by a Greek letter phi. Today I will be showing you how to find the nth Fibonacci number and how the Fibonacci sequence is related to the golden ratio. Shortly I will show you how to derive the value of phi, but first I'm going to begin with showing you how to construct the golden rectangle. The golden rectangle encompasses the golden ratio. So first I will start out with a rectangle with the ratio of 1 plus the square root of 5 all over 2. If we construct a square from using the shortest side of the rectangle, you will have a new golden rectangle. Construct a circle with center F and with the radius of the segment CF. Construct the arc from C to G, hide circle, and color the interior of the square. You can now create a tool to finish your construction of the golden spiral. When you construct your next square, you will have another golden rectangle. Therefore, each time you construct a new square with the length of the shortest side of the rectangle, you will get a new golden rectangle. Now we have our golden spiral. Now I will show you how to derive the value of phi. Construct segment AB. Construct a perpendicular segment to AB through B and must be equal to the segment of AB. Label the endpoint C. Find the midpoint of segment AB and label that point M. Use the segment MC as the radius and M as the center to construct a semicircle. Then extend segment AB to the semicircle. First I need to prove that B divides AE in the golden ratio, which will help me find the value of phi. In other words, I need to prove that segment AE over segment AB equals segment AB over segment BE. So with the construction, you can see that segment FB over segment BC equals segment BC over segment BE. Therefore, we have proven that B divides AE. Let segment BE equal 1 and AB equal x. Derive the value for the length of segment AB, which will be the value of the golden ratio. We know from my previous proof that segment AE over segment AB equals segment AB over BE. Then x plus 1 all over x will equal x. Set the equation to equal 0 and use the quadratic formula to find the value of segment AB. You will get x squared minus x minus 1 set equal to 0. The quadratic formula will give you 1 plus or minus the square root of 1 minus 4 times 1 times negative 1 all over 2, which reduces to 1 plus the square root of 5 all over 2, which is equal to phi. 1.61 is the approximation for phi. The golden ratio is an irrational number that cannot be expressed fully in a decimal form. That is why we use its exact value 1 plus the square root of 5 all over 2. By using the roots of x squared minus x minus 1 equals 0, we can find the nth value of the Fibonacci numbers. The roots are 1 plus the square root of 5 all over 2, which we will call phi, and 1 minus the square root of 5 all over 2, which we will call phi prime, where 1 plus the square root of 5 all over 2 is the golden ratio. As you can see, I have given some of the Fibonacci numbers 1, 1, 2, 3, 5, 8, and so on. Fibonacci numbers are a sequence of numbers such that every term is a sum of the previous two terms. Then f sub n equals f sub n minus 1 plus f sub n minus 2. If we were to take the ratio of two consecutive Fibonacci numbers, you will see that it will gradually get closer and closer to the golden ratio. Let's say we want to find the 25th Fibonacci number. First, let's go back to phi. What happens if we square phi? As you can see, by squaring phi, we get phi plus 1. Let's take phi to the third power. We get 2 times phi plus 1. If you continue to do this process, you will notice a pattern that the last term in each answer will become a Fibonacci number. Therefore, we get phi to the n power equals f sub n times 1 plus square root of 5 all over 2 plus f sub n minus 1, and phi prime to the n power equals f sub n times 1 minus the square root of 5 all over 2 plus f sub n minus 1. Now with these two equations, we can find the nth value of the Fibonacci numbers. Let's start with subtracting phi prime to the n power from phi to the n power. We can simplify the right side first. We can cancel out the terms f sub n minus 1. Then we can rewrite the equation. And now you can factor out the f sub n to get the following. Now set the equation to f sub n, and then if you substitute the roots in for phi and phi prime, you will see that phi minus phi prime equals the square root of 5. Then substitute the roots back in to get the formula for the nth Fibonacci number. This formula is called Bennett's formula. Now let's see if this formula is valid. Let's try finding the fourth Fibonacci number. Using this formula, we see that it is valid for f sub 4. You can see by the calculation for f sub 4 that it is equal to 3. Now let's go back to our original problem, the 25th Fibonacci number. Let's see what we get. As you can see, the 25th Fibonacci number is equal to 75,025. Now wasn't that fun? Now if we go back to the golden rectangle, you will see that the ratios are the Fibonacci numbers. The sequence of the ratios of consecutive Fibonacci numbers gives an approximation of the golden ratio. The further out we go, the better the approximation becomes. This shows that the size of the rectangle doesn't matter as long as the ratio is about 1.61, and you will have a golden rectangle. A man put one pair of rabbits in a certain place entirely surrounded by a wall. How many pairs of rabbits can be produced from that pair in a year, if the nature of these rabbits is such that every month each pair bears a new pair, which from the second month on becomes productive? No, rabbits never die, and new pairs are only born to pairs at least 1 month old. As you can see, as each month goes by, the rabbits are representing the Fibonacci sequence. Therefore, at 12 months, you'll get 144 pairs of rabbits. Now you have a fun problem to share with your friends. Thank you for watching.